speaker is Fran, who's a CEO and co-founder of Mastodon C, and has a brief experience working on big data projects, but specifically working on data science projects for the government. So look forward to your talk.
Great. Thank you very much. Good morning, just about. Hope you're all fully caffeinated and ready to go. I'm going to talk a little bit around the technical side of what we do here, and also a little bit around the context, because I feel like that's actually a very important part of doing data science well, and particularly we've always found that the context is in many ways more important than the technologies or the approaches that we're using. And we deal mostly with government, so my company Mastodon C has been around for 6 years now. We build and operate data science and big data systems using open source technology for a variety of organizations, mainly big organizations, so government or companies. And the reason that we set up the company and have continued to build it was that myself and my co-founder were working in big commercial organizations. So I was at Google, Bruce was at an investment bank. We were both thinking the technology advances and the data science advances we were seeing were incredible, and we were applying them to aims that we felt were not that interesting. So I was mainly trying to make people click on more ads. He was mainly trying to shuffle a bit of money around in an investment bank, and we're thinking this technology could do a lot in other fields. So we now exist to bring those technologies and approaches to fields where we feel they could have a lot more impact. Hence our focus on areas like government, which we feel using data well in government could really change people's lives and can actually make things much better for us all. So today I'm going to talk specifically about demand forecasting and capacity planning in government services. Sounds pretty dry, but it's a very important piece for government, because if they don't understand demand well and plan capacity well, then you don't have the right services in place for people, and then sadness ensues. So it's really important to use the data well, and unfortunately that doesn't always happen. So we worked particularly in cities recently. This is a lovely city. Data in cities is something people talk about a lot. You hear the word smart cities very often. It's not actually used that much, though, in city governments, or not used as much as it could be. So we've been working a lot on trying to help people change that. Actually, with the support of Innovate UK, who've given us some money. I have to say this because Innovate UK are in the room, but they've really supported us developing systems to try and get cities and the organisations that run cities to slightly grandiosely unlock the power of data for a better future. But I do really mean that can be done, and that's what we're working towards. We all in this room know we build models. They are boxes of one sort or another that take data in and produce something useful out. That's all well and good. It's pretty day-to-day building models. One of the challenges in government is that you often have different actors with different models and different data acting on the same people or places. So you've got the city government and the hospital, for example, both dealing with people, particularly, for example, if you're an older person who's frail or is in and out of hospital and social care, you get acted on by both of these systems, and they might both have different ideas about your data. They might both be planning services differently. If that's not coordinated, then things don't go well. So we've been building a system to share the data and the models that those organisations have. And as we've been building that platform, we've been trying to work out what models should be in there and come to the conclusion that actually demand forecasting and capacity forecasting is a really important thing for those big strategic organisations to be putting together. It looks like this. It's a web-based platform. You don't need to go into much more of the detail, but feel free to Google it and have a poke around if you'd like. But today I just wanted to talk more about a particular example of that demand modelling, because I think that's really important. And I said we've come around to the idea that demand and capacity is the most important type of model for us to build. There are a few reasons for that. So it's strategic. So the people at the very top are thinking about what their policy should be, what their budget should be. They're making decisions. The questions they are asking are about what's the demand going to be and what capacity do I have, and do those two work together. There's also a very pragmatic thing, which is PII, personally identifiable information, really important acronym in data science. If you're working with PII, you have a lot of ethical and legal obligations because you then know something about a person. Once you know that, you have to be super careful, both from a GDPR or DPA point of view, but also just, am I doing the right thing by a person? So if you're thinking at the system level, it's much safer in some ways. You have to still make sure your conclusions are accurate, but you don't have worries about things like edge cases in your predictions. And finally, in government, the population of the country, the services that we have, the budgets that government has, are all going through big upheavals right now, meaning that leaders in cities are having to make some big decisions. Some of them are really hard decisions, so they're cutting services or moving things around in ways they don't really want to do. That again means that using the numbers and the data well are even more important, because if they cut the wrong thing, that could be really damaging for people. So it's really important for leaders to have the right information and to be coordinating that information across themselves when they make choices. And the way that people try and do it at the moment, so in local government, they do already know that they need to do this, but it's a tough problem. If you're a person who's got Excel and no formal training in stats, it's really difficult to figure out where to go with this. So people might make assumptions about just doing trend-based, sort of year-on-year growth, or log trends or linear trends. A little bit of linear regression is probably about as far as it goes much of the time. That works in some simpler cases with things where you can treat all of the population as roughly the same and treat trends as fairly predictable. It doesn't work so well when things get more complicated, which is where you actually do need to start doing some proper data science type stuff. So the outputs that we need are complicated. Actually, small segments of population are more and more important as well. So taking the example of special educational needs, which is the one I'm going to talk about in a minute, there are at least half a dozen top-level types of special needs, and each of those is very, very different. And even within those segments, so within the autism spectrum, for example, some of those children will need residential care for most of their lives. Some of them might need just very light touch help at school, and you have to plan those services quite differently. So you can't just do a very broad brush, how many autistic children will there be? Okay, roughly we've got the right provision. You've got to be much more detailed. And the other challenge, which means we have to be more complex, is there are lots of discontinuities in the history of government services. So you can't say history has chugged along in a roughly linear way and will continue to do so, because every time policy changes or there's an upheaval like Brexit, either the population changes or the services change or something else important changes. So you can't look back for a long period and expect the future to continue in the same way. So it's all quite a complicated problem. And we've focused on a few areas of demand, but today I'm going to talk particularly about SEN. This is an area where local authorities, if a child has something called a statement of special educational needs, the authority is obligated to provide them with special support. So if a child's been formally identified as having those needs, there's then provision put in place for them. There are more and more of those statements happening, and at the same time, the authority's budget for supporting those statements has gone down. That is not a fun situation and requires some difficult planning and conversations, which is where we have to use data to run through the implications of different scenarios. And if we do that data better, then the decisions are better, and that's the point of this kind of thinking. And there are two things that you usually need to do. You usually need to understand future demand in order to plan future services. It's sort of simple, given the data, what's going to happen next. And then there's also the policy discussion. So if the senior leaders are sitting around the table and saying, what if we did this? What if we changed this service here? What if we did some early intervention there? Trying to think through what those proposed changes would mean in terms of their costs and their demand. So they're juggling a lot of factors. And again, using data to play through the implications can be really, really helpful. And SEN is really challenging from a modelling point of view. So it's really complex. There are lots of what we call need-setting combinations. So using that autism example, there are many different types of school that an autistic child could go to. So you've got in a standard authority, you've got maybe 10 setting types, 10 need types, and you almost complete that matrix with some child in every box. So you've probably got 100 combinations in a pretty normal situation. And also a lot of the cost is driven by a really small number of placements. So those children in residential care are driving actually quite a big chunk of the cost. So if you do a trend forecast and say there'll be 3.5 children with that particular need in this borough, that's not terribly helpful. You have to have much more probabilistic numbers and go down to very small numbers to get useful output. And there are lots of recent policy changes, which means you need something called a memoryless model, if at all possible, something which just goes from today as is, rather than needing to use a long history. So we've come around to doing this kind of forecasting using something called Markov chain Monte Carlo. This is a type of modelling that lets us run loads and loads of essentially simulations of how things might pan out, given some probabilities. We're quite well set up to do that because we're a big data company, so we can just chuck loads of servers at the problem and run lots and lots of different simulations until things start to converge. And then we can provide useful feedback back to those leaders about both what the most likely outcomes are in the next few years and also what the spread of probabilities is given the data that we have. So it's getting kind of complex to do this sort of thing. As you can see from this chart of how it looks, this is not the sort of thing that you would realistically do with an Excel spreadsheet. If you did, well, it's possibly technically possible. You would have quite a headache trying, I think, to try and do this. And we use a number of different inputs about what the population is at the moment and what the future overall population is. So the ONS or DCLG provide those. And then we create transition matrices, which are the spread of probabilities of moving from one place to another. And those are the real nub of how we do projections. So I'm getting a little bit techy. We won't get into too much depth here. But basically, the data that we collect is academic year, what kind of need, what kind of setting a child has, and how many children there are with those three characteristics. So this just about keeps us away from personally identifiable information as long as the numbers don't get too low in any of these boxes. So that keeps us a little bit away from doing individual level things. And then for each of those states which we describe, so which are described by those characteristics, we create these transition matrices. So given the child is in a particular state, what is their likely setting and need next year? And we use at least a couple of years of historical data from an authority to see what those likelihoods are. The intuition basically is that there is an expected outcome and then there is a spread of possible outcomes around that. The more data we have, the tighter that distribution gets. As you can see in the graphs on the left and the right, they're the same odds, but much tighter distributions as you add more data. And that's where you get more stability from the projections. And there's an extra challenge in things like SEND, which is where a little bit of the art comes into it. So sometimes things haven't actually happened in our data, which could in theory happen, and we need to incorporate those possible things into our transition matrices to actually get the right output. So there may be types of school that children could go to. We've only got maybe 5 children who've moved from a particular setting, so we haven't got the full range of possible outcomes because we don't have enough data. So we need to add in prior beliefs. This is a pain. This is where we tend to start speaking to the experts about what is in fact possible and therefore what sorts of priors would be sensible to add. And for our case, we just use the whole academic year and the whole setting and just forget the need type and use that to figure out what the possible, what are the odds of making a particular transition, and we just add that back in with the weight of one child, basically. So we get that binomial distribution of the beta of the data itself, plus that prior little tweak to allow for a pathway which we haven't actually seen. This is getting very techy, but stepping back, obviously because we're adding in lots of priors, we've got a complex system, we've got data quality which is probably pretty crappy. We have to step back and use lots of visualization. So if you take nothing else from this talk, take the fact that Sankey diagrams are awesome for complex systems and trying to work out what on earth is going on. So we draw all these kind of diagrams. So this is an example of, on the left bar in each of these blocks is year 1, on the right bar is year 2, and it just shows the count of children who moved from one setting to the other. So just lets you very quickly eyeball, for example, on the top left you've got further education, FEC, and to see where those children went to. And when we look at the real data, and our estimated things with different priors added back, and when we've modelled stuff into the future, what does it look like? It's much easier to say when something's gone screwy, when we've added back a silly prior, for example, or where something starts to go out of control. Again, this is much more about the art than the science, but they're essential safety nets, basically, when you're dealing with data of variable quality and policies which can change. It's really good to bring this back to experts in the SEN field, not in the data field, and talk them through it and see if anything feels wrong to them. So this modelling worked really well. So just to recap what I think we've taken away from it so far. So demand projection in government, it's really important, but it's really hard. So we've used statistically complicated methods, they're computationally intensive. Historical data in government is really hard to get hold of and often not of great quality, so memoryless approaches are really, really useful in this kind of context. There's some things which are possible but missing, so we have to incorporate priors, we have to use the Bayesian approach, which in these kinds of real life situations you really often have to do to incorporate beliefs in the technical sense, but also beliefs in the really belief sense. You talk to people who know the field and they say, no, I strongly believe that something is important. And then because the transitions are really complex, we just use loads of Sankey diagrams to review. And then stepping back one more level, the overall point of all this, why do we do it? We do it so that services are aligning closely to the actual needs that actual people have. And the upshot of all of that is that you get better outcomes for citizens and you get better policy decisions to realise all those outcomes. So I'm going to leave it there because I know we are tight on time. Do we have time for any questions, or are we going to?
Yes.
Okay.
Thanks for the talk.
Hey.
Say a bit about what it's like producing this kind of analysis for decision makers who are not data scientists.
Yeah, it's actually quite difficult to communicate the analysis well to decision makers. So confidence intervals, for example, they don't want to know about confidence intervals. They want to know what is the number. And if you're saying how many children with profound learning difficulties will you have in 5 years, there is no the number. There's a likely number and a spread. We use a lot of visualization. We use a lot of these things like Sankey diagrams to talk through with them. And we also make a real point of, when we start the project, sitting down with them to understand what they need so that we've got some trust by the time we finish the project and show them some numbers. They feel like they've engaged in that process. Even if they don't understand all of the black box stuff in the middle, they feel comfortable enough to work with those numbers. Because they're not stupid, they just don't know the technicalities. So it's a trust-building exercise more than anything. Hi.
This question is not related to the data science, but I'm really interested in how you're gonna manipulate the historical data. Like those data were not stored in electronic form, like they were like handwriting forms, and how you conquer that, you import that into your database in order to analyze those.
So if data is handwritten, there's very little we can do with it. We do work with text data a lot, so we often find that text data is a source which we turn into features by something like topic modelling, and then we use those features to learn from. So that's a really common use case for us.
And another question say those old data might store in, even though they were handwriting, but they might write in different tables or in different format.
Mm-hmm.
Is that come to be a big problems to your problem
It's a
solving?
massive pain, yes. Obviously the less structured data is, the more work it is to bring it into some usable structure. So it's always doable, but it's whether the investment of time and effort is justified in the circumstances. So in this case, in services cases, we tend to use quite simple topic methods. We've done some work before with things like insurance companies where they want to invest hugely more time to get more structure out of their data, and that's achievable. It just takes a lot of learning examples and a lot of refining of models.
Thanks.
Hi, the guy in red down the back.
Doing your projections on numbers according to the transition probabilities, do you assume that those are all sort of independent, or do you do something to account for the possibility that in a particular year more people make a particular transition en masse because there's something that's changed?
That's been a real problem for us, actually. So we've had to manually change transition matrices sometimes when we do an initial projection, and we talk to the head of service and say, look, it looks like everyone's going to pile out of this system into that system. They say, no, we just had this one-time thing. So we then have to slice the data differently and sometimes change the matrices by hand, actually, to incorporate different expectations coming forward. But yeah, it's caught us out a couple of times, actually, those data issues.
Thanks a lot.
Thank you.